This section of the book doesn't introduce any new concepts. It just starts putting everything all together so that we can start graphing functions. So we already know all of this material, is just combining it all together. Combining maybe some old Algebra 2 material along with the calculus that we've been learning. So the goal is to come up with a decent sketch of a function without a calculator, using algebraic and calculus concepts. So we're going to just try to find all these characteristics of this graph, starting with the x-intercepts. Well, the x-intercepts are x values that cause the y value to equal 0. That's going to be x equals 1 and x equals 3. So 1, 0 and 3, 0. Y-intercept, that's when x equals 0. So that's going to be negative 1 times negative 3 divided by 0. Wait, that doesn't exist. This is undefined at x equals 0. So we don't have any y-intercept, which leads us to the vertical asymptotes. Vertical asymptotes are x values that cause the denominator to equal 0, but not the numerator. That would be x equals 0. Horizontal asymptotes, that's when we allow x to go to positive infinity or negative infinity. And since we've got a leading coefficient of 1 for our x squared term in the numerator and also in our denominator, we've got y equals 1. That's what the y value approaches as x gets super big or super small. Well, the asymptotes do have calculus concepts involved in them. You learned about those before calculus. Finding the intervals of increase and decrease, that's actually a calculus question for sure. We're going to have to talk about the derivative here. So before we do that, let's keep in mind that we really don't want to take the derivative of this function in its current form because we've got a product in the numerator and something else in the denominator, so it's a product and a quotient rule. Let's see what we can do to fix this up in a much cleaner way. For example, we can distribute in the numerator and get x squared minus 4x plus 3. And that by itself makes it a little bit better, but even better than that, because we have a monomial denominator, why not just distribute the denominator and divide everything in the numerator by x squared? So we get 1 minus 4x to the negative 1 plus 3x to the negative 2. And then we don't need quotient rule or power rule. All we need, product rule, we only need power rule. So f prime of x equals 4x to the negative 2 minus 6x to the negative 3. The reason I found that is so that we can find the intervals of increase and decrease, so we'll set this equal to 0. When in doubt, take the derivative and set it equal to 0. Factor out the GCF of 2x to the negative 3. Remember, negative 3 is the smaller exponent, so that's going to be what we factor out. We're left with a 2x minus 3. So values that where the sign of the first derivative might change are at 0 and at 3/2. 0 because of the x to the negative 3, and 3/2 because of the 2x minus 3. So 3/2 will go here. X equals 3/2 causes our derivative to equal 0. We have a horizontal tangent line there. X equals 0 causes our derivative to be undefined. Well, that shouldn't be surprising because x equals 0 isn't even part of our domain, right? So letting x equal a negative something like negative 1, we'll get 2 times a negative value times a negative value, so that's going to be a positive. Negative times negative is positive. If we try something like positive 1, we're going to get 2 times a positive value times a negative value, so that's going to be negative. And then try something big like 2. We get 2 times a positive number times a positive number, so 3 positives makes a positive. Okay, so our intervals of increase, we've got 2. We've got from negative infinity to 0. And we also have from 3/2 to infinity. A small interval of decrease, that's from 0 to 3/2. Relative extrema, well, that happens on a continuous function when the first derivative changes signs. So we don't have to worry about x equals 0, again, because that's not where the function is continuous, but we do have to worry about x equals 3/2 because the function is continuous there. And the derivative changes from negative to positive, so the function changes from decreasing to increasing, so we found a relative min, and that's 3/2, whatever we get when we evaluate the function at 3/2. If you find yourself asking the question, well, should I plug that 3/2 into the derivative or the original function? Well, we already know what we get when we plug it into the derivative. We get 0. You'd be surprised how many people ask me that same question year after year. But yeah, we're finding the minimum of the function, so we're going to plug in 3/2 in for x into the original function. 3/2 minus 1 is 1/2. 3/2 minus 3 is going to be negative 3/2. Does that sound right? And then on the bottom we get 3/2 squared. Well, 1 3/2 is going to cancel out with 1 3/2. So we have negative 1/2 divided by 3/2. The 2's cancel out. We get negative 1/3. So that means that negative 1/3 is the y value. That is the relative minimum value of this graph. To find concavity, we have to take the second derivative. So take that first derivative and differentiate it. We get negative 8 x to the negative 3. And we get positive 18 x to the negative 4. Set that equal to 0. Factor out what we can. I'll probably factor out a negative. And then, let's see, a 2, I guess. And then an x to the negative 4. So this 8 goes down to a 4x. And this 18 goes down to a 9. So it's minus 9. And that is our second derivative in factored form, which allows us to find the places where the second derivative is either 0 or undefined. Once again, we have 0 because if our function is undefined there, our derivative is going to be undefined there, and so will our second derivative. And then 9/4 is going to be a place where the second derivative is equal to 0. 9/4 is, let's see, that's 2 1/4. So that's going to be maybe over here somewhere. I like to try to keep the scale on the f prime, double prime line the same as the f prime line. I just wanted to make sure that 9/4 showed up to the right of the 3/2. Not required, but it's kind of a nice thing to do. All right, so once again, same process here. Remember, this was the first derivative test, but this is not the second derivative test. This is just the concavity analysis. So let's see. When we have a negative 1, for example, we have negative 2 times, well, anything raised to an even power is positive. So negative 2 times positive times negative. That's a double negative, so that's going to give us a positive. And then something like maybe 1, we've got negative 2 times, again, positive 1. And then this is still going to be negative. So it's still a double negative. So it doesn't change from change signs there. But then when we go over to something bigger than 2, like say 3, negative times positive, that's going to give us negative. All right, so our intervals of concave up, we've got negative infinity to 0. We also have 0 to 9/4. And then we have an interval of concave down. That's from 9/4 forever. All right, so all of that information, I guess one more thing that I should have put here, but I guess I forgot to put here, is the point of inflections. Oops, I'll underline that. I'll underline that. So do we have any points of inflection? We sure do, at 9/4, right? So 9/4 is a place where the second derivative changes from positive to negative, so our function changes from concave up to concave down. We're going to try to find the y value there. That's going to be a bit messy. So f of 9/4 is going to equal, let's see, 9/4 minus 1 is 5/4. 9/4 minus 3 is going to be negative 3/4. And then divide that by 9/4 squared. So I think we'll have a negative 15 on the top and an 81 on the bottom. Divide both by 3 and get negative 5/27. That seems right. So negative 5/27 is the y value of that point of inflection. All right, so plot everything that we know. For example, 1 and 3 are x-intercepts. We've got a vertical asymptote. We've got a horizontal asymptote. No y-intercept. we don't really have any information about what's going on the left side of this graph, except for that it's increasing and concave up. And of course, we've got our asymptotes, so that must mean that our graph goes something like this. If you feel like plotting a few extra points to know exactly how close to the intersection it gets, you're welcome to, but this is probably good enough. All right, now our graph starts decreasing, right? It decreases from 0 to 3/2. So we know that we're going to decrease from positive infinity from that asymptote all the way down to our relative minimum. Turns out it looks like it's going to be an absolute minimum at 3/2 comma negative 1/3. So 3/2 comma negative 1/3 would be, I don't know, maybe around about right here. So we've got, this is all concave up and decreasing. And then it's going to stay concave up, but is now going to increase to 9/4 comma negative 5/27. That might be somewhere around here. So we're going to go ahead and still have concave up. Okay, so we've got this concave up section, and then somewhere around there it's going to change to concave down. It's going to continue to increase, and our graph is going to look something like that. Some people are going to get concerned about the fact that our graph crosses a horizontal asymptote. You are allowed to cross a horizontal asymptote, because horizontal asymptotes don't care about all that interesting stuff in the middle of the graph. Horizontal asymptotes talk about after all that interesting stuff is done, what happens as x goes to infinity, and eventually it levels off and the function approaches a y value of 1. But here in the middle, our graph does all sorts of other wonky things. I would point out that a couple other nice things that we could talk about on this graph would be domain and range. I think it's pretty clear that the domain is all real numbers except 0, right? So we could say negative infinity to 0, union 0 to infinity. And the range is something that we typically would have a hard time asking about back in Algebra 2, because we wouldn't have known how to find that minimum value. But at this point we can see that our graph goes as low as that y value of negative 1/3. So we have the absolute minimum is negative 1/3, and then it goes up forever from there. So that's something that calculus helps us answer that we couldn't really do beforehand.